Okay, so continuous, no breaks, no holes across the entire domain. You can draw it without lifting your pencil. And then discontinuous is going to have breaks in the graph. So for example, if we have a function that looks like this, whatever, that is continuous because you can trace that without lifting your pencil. Versus if we have something like this, so like these piecewise functions that we've seen, that is not continuous because there is a break in the graph where if you were drawing this, you would lift your pencil. Also, something if you just have a little hole, so like that, is not continuous. Okay, so any point where there's a break or a hole. There are 3 types of discontinuities that we're going to talk about. You need to be able to identify them with the proper vocabulary, and then we're going to also talk about how to identify them either on a graph or algebraically. So the first type is going to be an infinite discontinuity. So number 1 is infinite. What an infinite discontinuity is, in sort of layman's terms, is it is an asymptote. Okay? Is we will have some sort of a vertical line that extends through the graph of the function. So it might look something like this. When we talk about discontinuities, we're always talking about it in terms of the domain, so x-axis issues. This would have an infinite discontinuity at x equals 4-ish. It's a little bit off. Okay? Oftentimes you will see these sort of asymptotes, and it'll have 2. But we are talking about the x-axis. Okay? So we're not talking about that other asymptote that's going horizontal. We're just talking about the vertical. So we call asymptotes an infinite discontinuity because they go on forever, infinitely up and down. Okay? Removable discontinuity, and that's sort of the formal term. A removable discontinuity is a hole in your graph. So this is where we have something like generally the graph is continuous, but there's a place where it has a hole in it. Okay? So we call that removable because it's like just one point. It is not infinite going on forever in both directions. It's just one point along the graph that doesn't have a value. We typically see these in piecewise functions is what's called a jump discontinuity. So that's where you have, you've got your little graph, your little piecewise, and then it jumps along the domain. So like from here to here, we have a space where these 2 points don't equal the same thing. So there's a discontinuity there because we have a jump in the graph. When you have a graph like this, oh, hold on, I forgot to draw the hole. Okay, if you have a graph with a hole and you have another point beneath it, this is not a jump. Because it's a hole, this is a removable. So I just wanted to make that clear. This is still a removable discontinuity because it's a hole. Even though it looks like there's like a jump, because it's not that piecewise function, it is just a hole with a dot outside of it, we consider that or classify that look as a removable discontinuity. Can and will use algebra to determine types and locations of discontinuity if we can't see a graph. Obviously, everybody loves it when we can see a graph because it makes things super easy to figure out where things are going wrong or where things intercept x's and y's. But when we can't, we have to do it algebraically. So this is how we're going to find each of these types of discontinuity. You will have an infinite discontinuity, which is also what? An asymptote. Okay? You will have an infinite discontinuity when you factor it, top and bottom, you have no common factors in the numerator and denominator. So obviously, when we're talking about this, I just want to remind you, remember the two things we talked about where we're going to have issues are if we have rational functions. So we have an x in the denominator. This is where we're going to have domain issues. Or if we have square roots, right? So these are the places we're kind of looking. They should like flag something that like, okay, I need to figure out where I'm going to have an issue because I have one of these setups that's going to cause problems. So once you factor and you decide there's no common factors in the numerator and the denominator, you are going to set the denominator, so any factors in the denominator, because sometimes we'll have a quadratic, equal to 0, and solve for x. Okay, what you get for that x is where you're going to have an asymptote. For example, so if I give you this, if I just give you a function and I say, okay, tell me the type and location of the discontinuity in this function. The first thing that you're going to want to notice is that it's rational and we have an x in the bottom. So like when you see that we have an x in the denominator, that's like our red flag that we know that there's going to potentially be an issue. Because why? What can we not have in the denominator? But what number? 0, right? We can never have a 0 in the denominator. So we need to figure out what's going to give us a problem that's going to make our denominator 0. You can probably figure it out without doing the math. What's the problem here? When x is 3. But what we need to check for is to figure out whether this is going to be infinite, because when we talk about removable, we have to look for common factors. So factor the top. Okay, going back to our x method, right? 1 and 1. So this would be this. This is why we've been doing so much factoring work. Okay, do we have any common factors that are common to the top and the bottom? Yeah, we have 2 commons in the top, but we don't have a common in the top or the bottom. Do you see that? So we're comparing the two. Once we notice that, we say this is going to be infinite because it doesn't have a common factor in the top. And we set it equal to 0 and solve. This is where we're going to have an infinite discontinuity when x equals 3. Okay? And we're going to do a ton more practice with this. So like, don't worry if it's not like all sinking in at this second. Which we said we typically find in piecewise functions. So when you see a piecewise function, you're typically looking for a jump, but it depends. Okay, so like we said, most often in piecewise, what you are going to do is, because remember how we have, I'm going to write our little example down here. In our piecewise functions, we've got our brackets, and then we have our 2 or 3 or however many functions. If, and then they give us a domain restriction of some sort. So if we have our piecewise, what you're going to see is this, and you will have 2. They're typically going to give you the same number because that's where there's either going to be a jump or not. So we're going to check if 0 has a jump there or not, okay? Because that's where it's going to occur if it does. So you will plug in the given value. So in this case, it's going to be 0 to both or all, if there's more than 2, equations in your piecewise. If the outputs are the same, so if you plug in 0 and you get the same number out, what that means is that your piecewise function at 0 is coming to here, and then it's coming to here. And they equal the same value at 0. So if the outputs are equal, it's continuous. because those two piecewise functions are going to come together and meet at the same point, and it's going to continue through that point. If the outputs of the function are not equal, you're going to have a jump. Hold on, we get a bigger eraser. Okay. So if the outputs are not equal, you'll have a jump. So what that'll look like is your function will be coming up, whatever, to your point that you plugged in, and it's going to equal like 1. And then your other one's going to equal like 5. Meaning they do not equal the same value. There will be a jump at that point. Okay? So like for this example, if we plug in 0 to both of these, 0, absolute value of 0 minus 3, absolute value of negative 3 minus 1, 2. If we plug in 0 to the second one, 2 times 0 minus 5, so 0 minus 5. Are these equal? No. Meaning in this piecewise we would have what kind of discontinuity? A jump at x equals 0. Because that's where we plugged in, and we're always going to talk about them in terms of the domain along the x-axis where we have issues. Okay, last one, removable discontinuities, which are AKA a hole in our function. Occur when factored a common factor can be removed from the numerator and denominator. Okay, so here's our example. We'll do this in a sec. Okay, so it will make a hole in the graph when you set the common factor, so whatever that was that exists in both the numerator and denominator, equal to 0, and solve for x. Okay. For example, so in the top, what is this? How do I factor that? Difference of squares. Okay, you will start seeing this. It doesn't ever go away. Don't ever forget about difference of squares. So we must factor the top to look like this. X plus 6, x minus 6, because it's difference of perfect squares. So what do you notice in the top and the bottom? We have a common factor of x plus 6. That means that we are going to have a removable discontinuity when this factor equals 0. Because we know we're going to have an issue because of the denominator. We also always have to look at the numerator to see if it's going to be an asymptote or if it's a hole. So it's a hole when you have a common factor. And the hole will happen when this common factor is set equal to 0. So we will have a hole on our domain when x equals negative 6. What do you think we're probably looking for? A jump. So what we want to do is take that negative 3, because it's asking us, is it continuous at x equals negative 3? So we got to plug that into both. So we get 3 times negative 3 is negative 9, minus 2, negative 11. And then we'll plug it into the second. 2 minus negative 3. 2 plus 3 is 5. Those do not equal one another, which means what happens at x equals 3? Yes. There is a jump at x equals, negative 3, not at 3. Because those values are not equal. So what this is looking like on a graph is that at negative 3, one function is at negative 11 here. But then one function is up at positive 5. let's call this -3. Graph's not drawn to scale. Is this continuous? Correct. So what this is saying is that when x equals 2, one function is heading towards +1, and another function is also at +1 when x equals 2. So we would say this function is continuous. So the first thing we notice about this is it's rational. We have an x in the denominator. That means we're going to have some sort of domain issue because we have an x in the denominator. First thing we should always do is what? Factor, right? We always want to get things in factored form. The bottom is what?
X plus 3x.
Good, it's the difference of squares. Okay, this one specifically gave us a value that it wanted us to talk about. It says that x equals -3. Notice what we have here. What kind of discontinuity is that going to be? A whole, a removable discontinuity when we set this equal to 0. So we will have a removable discontinuity at x equals -3. And this is how you're always going to talk about your discontinuities. What is it and where is it in terms of x? Notice what else we have left, though, in this denominator. We have another problem when x equals what? Set it equal to 0 and solve. Now this denominator does not have a common factor in the numerator, meaning what kind of discontinuity will this be? What did we say? When it has no common factor in the top, what kind of discontinuity is it? Asymptote, right? It's going to be infinite at x equals 3. So this graph will have multiple discontinuities because we have multiple issues in our denominator. And we can see that by factoring. Okay. Okay, sometimes you'll see this. Number 4, f of x equals 2x plus 7 at x equals 8. Are we going to ever have any discontinuities along this function? No, why not? Because it's linear. Linears, by definition, just continue in both directions forever and have no domain issues. So will it be continuous at 8? Yeah. Will it be continuous at any value you ever plug in? Yes. So we just say continuous. So again, sort of going back to what we talked about last time, my expectation is that you understand parent functions and you understand that, like, without issues in the denominator or underneath the root, you know it's continuous. If it's quadratic, if it's linear, if it's cubic, like, we don't have any domain issues. We have domain issues when we have denominator problems or square root problems. Okay, let's try this one. Okay, where are we going to have an issue? When the denominator equals 0. So set the denominator equal to 0, solve for x. What kind of discontinuity is going to happen at x equals 9? Can you factor this? It's not a difference of squares, yeah, because x isn't squared. It would be no, because removable has to have a common factor. Right. Do you guys see how this doesn't have a common factor top and bottom? Meaning this is infinite. Okay, at x equals 9. What about at x equals -5? Is this going to be continuous at x equals -5?
Yeah, probably.
If we plug in -5, what is this, -14? Do we have any issues with that? No. The only reason we would have an issue is if we had a 0 in the denominator. So we're just going to be talking about essentially where is the function going in either direction. Okay, the notation for end behavior is almost always the same. To the left, we are talking about as the x approaches negative infinity. That means to the left on, the graph, as x approaches negative infinity. So these two go together. Negative infinity means to the left. That's the left on our graph. as x approaches negative infinity, then we talk about where is the function headed. Okay, either negative or positive infinity, or potentially it'll approach an asymptote. Okay, so then end behavior to the right, Tyler, meaning in a positive direction. So to the right, these two go together always. And then we will look at the arrow and see where is the function headed. Let's look at this one. This purple graph. I don't know if it's purple on yours, but okay, end behavior. We're going to first talk about it to the left as x approaches negative infinity, because that's always how we start end behavior, to the left. Good. The function is also approaching negative infinity because that left arrow is headed toward negative infinity. And then on the right, as x approaches positive infinity, so heading to the right, our function is approaching what? Also positive infinity. So looking at the arrows to the right, to the left, both are approaching positive infinity. That's really smushed. Yes. Okay. How would I write the third one? As x approaches negative infinity. Tyler, where's my function headed? Where's my function headed?
Positive.
It is also approaching negative infinity. Both arrows are headed in a negative direction, so on both sides. Specific number value rather than positive or negative infinity. So like, look at this example. This has technically two asymptotes. Okay, we got one there and we have one there. So be super careful when we're talking about end behavior here. As x approaches negative infinity, meaning to the left, where is our function approaching? It is approaching 0. Do you see how this graph is going to get closer and closer and closer to 0? It is never going to cross 0. It's not headed to negative infinity because it's never going to cross that asymptote. So the end behavior to the left is it's getting closer to 0. And then as x approaches positive infinity, so to the right, where is our function headed? Sorry, I meant to do this as an arrow. Approaches 0. F of x approaches also, where does it approach? 0. It is not going to positive infinity because it is never going to cross that asymptote. So you have to watch for that as well. This will be more for now. For now, this is going to be graphic. You won't know how to do this yet algebraically, but someday you will. What a day. So luckily on this, it's super nice. You have a graph. So using this graph, there is an asymptote here. There's an asymptote here. There's also a hole. So there's a lot of things happening. First, it asks us for the type and location of discontinuities. Okay, so, but how do we call that with our good vocabulary? Removable. A removable discontinuity at x equals. Do you see how there's a removable discontinuity here when x equals?
That one makes sense.
3. There is also an asymptote here along the axis. Remember, we're talking about discontinuities in terms of x along the domain left to right. We have a infinite discontinuity, which is an asymptote at x equals 0, left to right. Okay? So hold on. The y is what we talk about with end behavior. Because we also have this little situation here with our horizontal asymptote, which is going to affect the end behavior of our function. So discontinuities are x along the domain. End behavior is where we talk about potential horizontal asymptotes. So to the left, as x approaches negative infinity, where is our function headed? To positive 1. It is going to always get closer and closer to that asymptote. it'll never cross it. So that's where the end behavior heads. So then to the other side, as x approaches positive infinity, to the right, our function heads toward 1 again. Okay, last one. Huh? What? Here? How is this infinite? Does it go on forever, or is it just one point? It goes on forever. It's an
arrow. It's just
asymptotes does not mean the function is not continuous. Do I have to lift my pencil to draw this function? No. So it is continuous. It is continuous. Because the definition of continuous is that it does not contain any breaks in the graph. The graph is coming from here, and it is continuing forever here. We do not pick our pencil up to trace this. It is continuous. This is just an exponential function. There is no issues on an exponential function. Yes, there are places where it'll never hit, but it doesn't disrupt the graph itself. So to the left, as the graph approaches negative infinity, the function is going up forever. So to the left, it's going to infinity. To the right, it is heading toward that asymptote. That horizontal asymptote is stopping my function from getting any lower. So it is heading toward 0 on the right.